Today we have the pleasure to hear from Rogério Capobianco from Brazil, who will talk to us about photon rings and shadows of Kerr black holes immersed in a swirling universe. So as usual, there will be time for questions at the end, but if you have questions also during the presentation, feel free to ask. Either unmute yourself or raise your hand or write in chat, and then I will forward the question. So thank you again, Rogério, for being here, and the floor is yours.
Right. Thank you for the invitation. It's a pleasure to talk to people in Aveiro. You can also see my mouse, right?
Yes.
Yeah, you're seeing my full screen.
Yes, yes.
So, well, my name is Rogério Capobianco, as Rodan said, and I will talk about photon rings and shadows in the Kerr black holes immersed in a swirling universe. So, basically, what I will discuss and present today is on this paper on arXiv. And these results have been found in collaboration with Beth Hartman, Jutta Kunz, and Nikita Vaz. All right, so let's get started. This is my, oh, it does not work. Okay. So this is my presentation. I will initially talk a little bit about the space-time, some motivation words, and then talking about the geometrical properties of this particular solution. And then I will directly go to the physics that I want to discuss, light rings and shadows. So I will give a small, simple presentation to the methods, and then present the results, and then conclude. Okay, so let's start. So the swirling universe is an exact solution of the Einstein field equation that represents a rotating background. I know that some people in Aveiro have worked in this solution as well. So this solution, although it was presented in some older papers, the metric tensor appeared in some older papers. Well, people started to study it around 3 years ago, more or less. When they study the physics that are applied to this particular space-time. And it can be obtained. It was recently re-obtained, let's say, by applying the Lie point symmetries to the Einstein field equations, particularly on by exploring the Euler's transformation in a NS formalism. I will not exactly talk about the generating techniques in which the solution was found, but just to mention how the solution was obtained or re-obtained. And very often it has a relation to how the Melvin-Bono magnetic universe was found, because the process is exactly the same, to be honest, or it can be at least. So the swirling universe is obtained through application of the Euler transformations, and we obtain the swirling universe, and the black holes emerge in the swirling universe in a very same fashion as the Harrison transformation generates the Melvin-Bono magnetic universe, and black holes immersed in this magnetic universe, magnetic background. And so we are talking here about the Kerr black hole immersion in a swirling universe. So we also need to talk about the Kerr black hole. And the Kerr black hole, I believe everyone knows what it is. It is a rotating background that is only characterized by two parameters, the black hole mass and the black hole rotation. And well, it is believed to be the end point of the life of a star collapse. So every isolated object in our universe is expected to be described by a Kerr metric, a Kerr solution, basically, at least in this Kerr paradigm. And now we are in my presentation. I will talk a little bit about new geodesics. So photon rings and shadows are basically the study of new geodesics. And this has been particularly interesting recently with all this black hole imagings and discussions on that sense, on that regard. So let's start to talk about the solution itself. So the Kerr black hole immersed in a swirling universe. So here we have the metric tensor describing the Kerr black hole immersed in a swirling universe. So in my next slide, all these functions will be defined for completeness, but what I want to particularly focus here is that the swirling parameter that here is called J is enters in my metric within this fancy f function and this omega function. These two functions are directly related to explicitly related with the swirling parameter here, and both of them are going to order 4 in J, let's say. So this is basically the metric that I want to that we will discuss. So we have obviously the two limits. So when j goes to 0, we recover the Kerr solution. So when the swirling background is turned off, we recover the Kerr solution. And when the black hole parameters like mass and the black hole angular momentum, the Kerr parameter A goes to 0, we recover the swirling universe. Sure, if you keep m and put a equals to 0, you have the Schwarzschild swirling solution. Okay. Before here I have all the functions to the metric functions explicitly written. But before I talk about,
Rogério, can I ask a brief question? The previous slide.
Yes.
Right. So if you put m to 0 but not a, so is it still the swirling universe in some kind of different coordinates? Like if you put m to 0 in Kerr, you get flat space-time in oblate coordinates?
It's not the swirling universe, but what I'm calling swirling universe here is the one that depends exclusively on J. If you set m equals to 0, you still have a strange coupling between these two angular momentum structures, J and A. But at least as long as I am aware, you are not able to construct the swirling universe metric in some strange coordinates. Could be the case that you have some very fancy, non-trivial transformations that do this mapping, but I believe it's not, absolutely not. And I have not checked the scalars to really say this is not necessarily, but at least on the level I have studied, you do not recover the swirling universe. But it is something immersed in the swirling universe. Something is like a rotating stuff.
So,
does it answer the question?
So if I understood correctly, you were saying that if you put m to 0, it's not just the swirling universe in some strange coordinates. There's extra structure there. It's a different space-time. But you're
I
not
believe
sure
that,
it's
yes.
non-singular everywhere or something like that.
Yes, exactly that.
Okay. Thank you.
Thank you. Okay, where do I go? Okay, so here's the okay. Before we're talking exactly about the Kerr in swirling case, I would like to talk a little bit about the swirling universe, and let me define the names I'm giving here. I'm exclusively calling swirling universe the one that I will present it here. So this matrix, what I'm calling swirling universe, precisely. So, and why I wanted to talk about that is because this solution itself, the swirling universe, even in the absence of any compact object or any compact or anywhere that is immersed there, just the swirling background itself, has some interesting properties, some interesting features that are inherited to the other solutions once black holes are immersed in it. So first of all, this solution does just swirling background is station is axially symmetric. Obviously, here is writing in like cylindrical-ish coordinates, but doesn't matter. What I want to discuss that here we have a GT phi component that is different from 0, and this is why we have this sense of rotation in the space-time being very explicitly. One particular characteristics that appear in this space-time, and as long as I'm aware, continue to appear in all other spacetimes that are representing swirling universe, is that this solution has algorithms that are not compact. They actually goes from the c equals to 0, the equatorial plane, all the way to infinity. So you have less extended surfaces of the algorithms. And this will also appear later in the slides. I will show this for the Kerr case, and then I will point it out what is from the swirling itself and what's for the black hole. And the other aspect that is quite fancy is that, and we can see that exactly for this term, that the frame dragging of this space-time is like linear in z in those coordinates. and then we can see that we have a different in the sense of rotation once we are in the upper or the lower section of the space-time. It actually counter-rotate with respect to each other. And this is a particularly interesting feature because this affects the geometry, the effects of a test particle that are traveling around the space-time, either for the swirling universe or once black holes are immersed. That this is a thing that you should keep in mind when you're dealing with test particles. Yeah, that's it. And then, well, beside of that, the swirling universe itself, in the absence of any compact object, is like absent of singularities, conical singularities, or any pathologies like CTCs and this stuff. All right, so it was just one slide mentioning the swirling universe, mostly because today I want to present these two characteristics that appear on the swirling universe. Now let's go to the black holes. The K black hole immersed in a swirling background inherited some properties from the swirling background.
Sorry, may I ask a question?
Yes. Yes.
So what you were saying before with these two halves that rotate in different directions, so does that mean that you can say if you are in some point of this universe, you can tell in which half of the universe you are, and that there is a like special region also in between that is kind of like doesn't depend on the coordinates in a way, but it's really like a physical location.
Not that depends on the coordinates, but in principle you could, if you have the properties, if you know that you are in a universe with like positive J, and you know the numerical the sign of your frame dragging, in principle you can say if you are in the upper and the lower hemisphere. Yes.
Okay, thank you.
Okay. Okay, sorry. Okay, so going to the black hole immersed in the swirling universe. So some characteristics, once we immersed a Kerr black hole in the swirling universe, some characteristics inherited for both solutions, particularly when we consider some small values of the swirling parameter. So another thing about the swirling parameter is that when talking about the geometrical properties or the particle motion, the swirling parameter kind of dominates the dynamics of the particles, of the dynamics. So even when you consider some small variation of swirling parameter with respect to A, for instance, you will see significant difference. And when A and J are comparable, the swirling is absolutely dominating. This will be obvious coming in the coming slides. So the Kerr black hole, different from the swirling background, the Kerr black hole immersed in the swirling universe has this irremovable conical singularity on the axis. And here we have the two deficit angles that we can obtain by calculating the difference in the circumference and the radius on the axis. And then we have these two deficit angles on theta equals to 0 and theta equals to pi. And you can see explicitly that they are not removable. At the same time, you could do some transformation to remove one of them if you want. And here is also interesting that we have this critical value in which one of these angles diverge. And also that the conical singularity is only present once we have AJ and M different from zero, finite AJ, finite A and M different from zero. So this means that basically, if you are the Schwarzschild swirling case with A equals to 0, you have no conical singularities and all the other special cases as well. And this critical value is important. So every time I'm talking critical value, I'm talking about AJM equals to 1/4. Okay, so the event horizon. So the presence of the swirling background affects, so this black hole also has continued to have an event horizon, and due to the presence of the background, this horizon is deformed. And here I have some embedding. This is a different paper, but some embedding of the structure of this horizon. So which becomes a slightly more, I mean, this is the pure Kerr case, which we know is like the Tori oblated, sorry, and then by adding the swirling background and increasing the value of J, we start to see these things more deformed on the axis. Okay. And now talking about the ergo regions, because I talked about the ergo regions for the swirling background. Now I'm talking about the ergo regions for the Kerr case. We know that the Kerr case, the Kerr black hole itself, has this compact ergo region around the event horizon. For when you consider the Kerr swirling case, the ergo regions, particularly for small variations of the of J, we have these two structures appearing kind of independently, let's say in a superposition-ish structure. So this is what I mean. So we have here these extended regions that are not this non-compact extended region that comes from the swirling universe here. And then we have around the event horizon this compact ergo region coming from the Kerr case, inherited for the Kerr solution itself. And this is for, well, a quite small value of the swirling parameter. When we increase the value of the swirling parameter, we see that these extended regions like approach more and more the event horizon until eventually these structures merges here, for instance. And by increasing further the value of the swirling parameter, the full space-time has a cylindrical-ish structure on the ergo region, going from -infinity to infinity. We noted as well that for the solution, okay, so here the colors represent the velocity within the ergo region. Red is negative velocity and blue is positive velocity. And once we reach and cross the critical value that I mentioned before, like AJM equals to 0.25, the ergo region are always in a full merge, and they are always co-rotating with respect to each other from -infinity to infinity. There's just one velocity within the ergo region. Okay. Okay, so that's the general presentation of the geometrical properties of space-time that I wanted to discuss. Now we are going directly to the light rings. Okay.
Sorry, may I ask another question?
For sure.
Just as a curiosity, this AGM is 1/4. Is it like a limit that you cannot go beyond, like say the limit on the Kerr parameter, or is
I would not say you cannot go beyond. You can go beyond the point that you at exactly this value you might have you need to take some attention, something diverge, but you can go beyond that number, yes. Okay. But the space-time changes for AJM smaller or smaller than 1/4. The space-time has some differences if you go beyond, but depending on what you are discussing, it's not so relevant, to be honest.
Okay, so it's not like a naked singularity.
Yeah, no, it's not a limiting case.
Okay.
There are differences, geometrical differences, but it's not limiting case. They continue to exist, well, as the solution exists, at least.
Okay, thank you.
Okay, thank you.
Can I ask a follow-up on that? So you showed us before that the deficit angle was diverging at some value, which was exactly that one, right? So
exactly.
But then you would have one of these deficit angles to be infinite. What does that mean when you get to that particular value of AGM equals 1/4?
I have no idea, to be honest. I really don't know. I never went too much far on this study of this conical singularity-ish stuff, but I don't know if you have, like, if you do explicitly this choice, you would have one of these deficits going to infinity, but I don't know what this means, to be honest. Sorry.
But yeah, but in your lensing, that was never something problematic.
Where?
When you were studying your lensing, so taking this value. So if you have a conical singularity, of course, I mean, at the axis, when this conical singularity is, you have geodesic incompleteness. If some geodesic
Yes.
would get there, you have to deal with this. Now, the fact that the deficit angle becomes infinite doesn't provide further obstacles. It's just the same. You have to be careful if some geodesic would get to the axis. Is that it? Or was there any extra obstacles if you'd go to this type of value?
Well, probably, but the point is that from the integration of the new geodesics, we never went that close to this value, to be honest, and you kind of have a limitation on that regard, because in order to have like the shadows and lensing images particularly, you need to choose J very, very small, so you are completely far from that value, to be absolutely honest.
Okay.
But sure, a full analysis of the geodesics, you need to consider the full spectrum of the parameter spacing, and so on, and it some problems may raise, I don't know.
Okay, thank you, Rogério. Thank you.
But yeah, for the shadow analysis, up to the point we have done, in order to really properly integrate the geodesics that they don't explode numerically speaking, we must fix the value of J considerably small, to be honest, with respect to A.
Okay.
All right. Where I was. Okay, so light rings, let's start about light rings. Light rings are closed circular new geodesics, basically, and we will discuss it in using the potential formulation. The potential formulation, I believe everyone here, well, I'm not sure if everyone knows it, but it was developed in Aveiro, or in collaboration with people in Aveiro at least, with Pedro and Carlos that are here. I will just give some general overview on that. So basically, we have the Hamiltonian formulation to describe new geodesics, or well, particle motion in general, and then we separate this Hamiltonian in two parts. Let's say a kinetic part and a potential formulation, a potential part. The kinetic part just have the radial and the polar momenta, and everything else is thrown up to the potential. So here we have the general potential, in which E and L here are the two conserved quantities that we have for particle motion, that are very often related to energy and angular momentum. But even if you don't call this way, they are the conserved quantities due to the space-time symmetries. We can take this potential and rewrite it in a more interesting form, which is this one, by introducing the impact parameter. And what's interesting here in this equation number 8 is that we have the introduction of these two potential, 8 plus and 8 minus, which depend only on the metric component, does not depending on any orbital parameter like the energy and angular momentum that I mentioned before. So it's basically the property of the space-time itself. And to study light rings, which are planar circular orbits, planar circular new geodesics, we imposed these conditions, which basically on the level of the 8 plus and 8 minus potential, we have this set of equations. So these are the two equations that we need to solve when dealing with light rings in stationary axially symmetric spacetimes. All right, so for our case in the Kerr-Swilling, these two potentials take this quite simple form. Here, remember that 8 and F are slightly complicated functions, but because of that, we need to do a complete numerical analysis to find the roots from this equation. And okay, so objectively, what we are looking for here is like we have this potential, and we are looking for pairs of r and theta that satisfy the gradient of this potential equals to 0. This is exactly what we are looking for a fixed value of J. So we have done that numerically, basically setting a grid and varying J and looking for all the possible solutions to that equations. So just mentioning a little bit about the light rings, I think everyone probably knows that, but just to reveal it, though, the Schwarzschild black hole has one light ring at r equals to 3m, and this one is on the equatorial plane for the geometry. The Kerr black hole has a pair of light rings also on the equatorial plane. I have not put the mapping here, whether the radians which you can find it, but you can also find that analytically. And the presence of the swirling background overall drags out or pulls out particles from the equatorial plane. So this does not mean that we cannot have planar motion. This means that it's not easy to find equatorial orbits necessarily. All right. So for a equals to 0, 0 for the Schwarzschild-Zwilling case, it has been shown by Moreira, Zeus, and Carlos in collaboration that the light rings exist, but they are outside the equatorial plane. For the Schwarzschild-Zwilling case, once we impose a equals to 0 in the Kerr-Zwilling case that I'm discussing, we have this extra symmetry here on the two potentials. And this is interesting, and because here you have the distributions of light rings in the theta r plane. We started here on the equatorial plane with r equals to 3m, and where the Schwarzschild one is for j equals to 0, and as j increases, you are starting to have a pair of light rings that are on the same radial distance, and the equidistant here in the theta direction. You can find these pairs, and as j increases, the light rings approach the horizon structure and the axis. This is what happens for the Schwarzschild-Zwilling case. Well, what I'm also showing here is exactly the spatial distribution of r and theta with respect to j. This does not mean that r is a function of j directly. This is just the solutions we are plotting the radial distribution with the j parameter. So in here we can see that for the Schwarzschild-Zwilling case, the two are exactly the same as expected, and then in theta they are like equidistant with respect to the equatorial plane. All right. Once we increase the value of a for any a different from 0, we started to see that the distribution of light rings appearing are very different. So here we need to note that first of all, we noted that on the equatorial plane, the Kerr solution by itself with j equals to 0 have two different located light rings, and these two branches, let's say like branches of light rings, started on those light rings for the Kerr case. What is interesting here is that even for smaller values of a, as we increase the value of a and j, we started to see that a third branch of light ring appears for larger value of the radius and around the axis, and this light ring also moves as j increases. There's one possible existence and location of light rings moves inwards in the direction of the event horizon and on the axis. Here we have as well is the image too small? It's possible to see it. I can give a zoom if it's small.
We can see it.
Okay, so okay, well, if someone is not seeing properly, say it and I can give a zoom. So here we have the radial and the polar distribution, let's say, and here we can see that this is for a equals to 0.2, so like considerably small. We see that the radial distribution starts too distant one from each other, so we have these two branches, let's say, and the third branch appear here for a larger value of the Swilling parameter. And well, yes, and here we have what is particularly interesting is that for sufficiently large value of the Swilling parameter, we have a small region in which up to 3 light rings can coexist, and this is what this colored region here says. So if you see that here we have like three light rings coexisting for this very same value of AJM. And we found that this happens for all values of A we have studied with a full spectrum. You just need to have J sufficiently large. And particularly interesting is that this third light ring starts to appear here once we reach that critical value. So once we have AJM around equals around 0.25, we have the appearance of this third light ring. Here we have the same plot for happily rotating black hole. Remember again, we have like in the equatorial plane, there's two light rings for care, and as J increases, this light ring distance itself. So here we have the radial and the polar distribution again, and we have like they started here, and then we have the third branch appearing for a larger value of the radial distributions, and then moving inward in the radial direction. Another thing that is particularly interesting is that although here we have this range in which we have the three light rings coexisting, the light ring that coming from the light ring that comes from the H plus potential here starts to disappear at the end of this region as well. So after that, we have like just two light rings coming from the H minus potential. Okay, so this is overall the summary of the light ring. So for any value of A different from 0, we have a break in that symmetry on the potentials. The light rings no longer happens at the same value of the radius, and we have the third light ring branch appearing once we reach the critical value HM equals to 1/4. The third light ring always emerges from the H minus potential around the pole for a larger value of R, and as J increases, this light ring moves inwards around the horizon and the axis. Oh, sorry. And well, the third light ring exists in a range of the swirling parameter, since as by increasing J, the light ring coming from H plus disappear very soon after the appearance of the third one. For sure.
So can you elaborate a little bit about this critical value? What happens exactly at this critical value? Is there a change of the asymptotics, or a change of the total topological charge of the light rings? Can you comment on this? So what corresponds to the change at this critical value exactly?
Okay. It's quite uncomfortable not knowing who I'm talking about, because I don't know your voices.
Sorry, Rogério, it's Pedro Cunha.
Okay, Pedro. So here, it's not exactly clear what precise or everything that happens at this value. We can say that exactly at this value, regardless of the sign of J, because you can particular here I have choose J positive for all the plots, but you can have similar if you set J negative. We can say that, okay, we have a divergence for this deficit angle. This is happening. Besides that, we have explored a little bit of that, but we don't have concrete observations on what else is happening on that specific value. The asymptotics is something that we have looked at, particularly speaking, and the asymptotics of this spacetime, I need to go back a lot of slides here. The asymptotic of this spacetime is also not as obvious as it may look like, because we may think, and we thought about that on the beginning at least, that asymptotically from the as we go asymptotically far away from the black hole go to infinity, we have just a swirling background. There's the presence of this black hole vanishes, because makes sense. But this is not what happens, because here, if you look to the terms with omega 2 that are goes with J square, we have considerably large powers of R and the theta distribution as well. Theta distribution is less trivial to visualize, but we see that we will have still participation. So the asymptotic behavior of this spacetime is not as obvious to say far away from the black hole is just swirling. In a very similar fashion as far away from the Kerr Melvin solution, you still have elements of the black hole. It's not just the Melvin background, the magnetic background. But talking specifically about the critical value, if you analyze the how this behavior, these functions behaves by setting by setting your space-time to have exactly that combination. You see that this function, that critical value also appears in this function omega 2. It is not trivial. They need to do some algebra here, but you can always find that very same relation by AJM by dealing with the term that is dominated by omega 2. And that was particularly interesting. However, we don't have any big problem like things diverging or anything like that. You just have you can find that limit by the conical singularity. You can also find a limit if you assume that omega 2 is the dominating term. But that don't say much. That does not say much on the geometrical properties of the spacetime. We try to analyze as well if we had some type of, and nothing that I'm talking here is on the paper because this was not complete findings. We also try to analyze what's happened if we could see something on the scalar curvature and things like that, which was particularly complicated because although the metric is analytically given, we could not find those quantities analytically speaking. You always need to do, we did an numerical analysis then, but apparently those things are kind of well behaved on that value as well. At least finite, not exploding, not diverging or anything like that. One thing that was very interesting, and we had no idea what this meant, to be honest, was that the Gaussian curvature had appears to have a divergence on that value for all the values we have tested, but we have no idea what that means. And I know that I have not answered your question because I talk a lot of things that are unconnected, and I kind of lost myself. Sorry.
It's okay, Rogério, but I think in the middle of conversation, I think I understand more or less. I think I suspect what's going on. But yeah, please continue. I don't want to for you to lose too much time on this question as well. But I'm happy. No, I'm happy at the moment.
Okay, because we don't know exactly everything that happens on that value. That's the point, and we are also curious. So we discuss a lot of things, and I have this in my mind. So I just throw up a lot of words here. Sorry, and I'm glad you understand something.
Well, I'm not saying that I understand is perhaps an overstatement. I suspect something. So instead of a change of the topological conditions of the boundary conditions at infinity, I suspect there is a change of character of the effective potential close to the axis because the conical deficit changes sign, and there is in a discontinuous way apparently at that value. That is my understanding. So I guess the orientation of the gradient might change direction. I don't know. That is my suspicion. But yeah, so probably this amounts to a change of the global character close to the axis. So yeah, but not an understanding, just a suspicion. But I'm happy for the moment.
All right. But yeah, well, we don't have a full understanding on that. But what I can say is that on the physics we are trying to analyze here, we see that this value is important because we do see differences overall in the space-time, either in the light rings, like the third light ring appearing, or the ergo regions merging and have the same velocity, and so on. I have no idea where I was, so I'm sorry. Where I was. Okay. Okay, so this at the critical the third light ring starts to appear once we reach that critical value, and then we have the small range in which three light rings coexists. The next question is the next point that I want to present is exactly because I talk a lot about the ergo regions, and a particular feature on the Swirling background is exactly these extended ergo regions. So the question for us was, where does these light rings are on the space-time once these ergo regions are expanding and expanding, and we eventually by increasing the value of J and then allowing the third light ring to appear eventually, we see that these light rings are always going inside the ergo region. They are always existing inside the ergo regions. And for the values we have studied, within the values we have studied, the three light rings configuration are always coexisting inside the ergo regions. And these light rings are always, at that stage, the light rings are always co-rotating with the swirling background if you are like below and above the equatorial plane. And that's it about the light rings, the planing, the mapping of the light rings. Now talking a little bit about the shadows of this space-time. So to study the shadows, the gravitational lasing in the shadow of this black hole, we did integrate the equations of motor, the new geodesics, using the pi-hole package. The pi-hole has also been developed in collaboration with people in Aveiro. So I'm not talking exactly about what the package the dynamics, the numerical dynamics of the package, just what we have done with that. So in overall, the new geodesics are integrated backwards in time from an observer position until it reaches what it's called celestial sphere. And here we have a schematic representation. So here we have, for instance, a small observer looking to the sky, let's say the celestial sphere, and this observer has like this field of view here. So by looking to this observer, and like by integrating the new geodesics in a given geometry in which we set this observer and this celestial sphere, this sky sphere, this observer will see something, let's say. So in here we have some images of what this observer would see if this observer is living in a Minkowski space-time. You just see like this flatted sphere, this flatted region sphere. And if this observer is living the swirling universe, it starts to see things more, well, swirled. That's it too. I'm not sure this word means, but like twisted. I think that was the word that was using before the Schwarzschild case, where the shadow is like twisted. And we see that even if you consider the swirling universe in the absence of any compact object. So when we have compact object, the compact object is said to be here at the origin of this celestial sphere. So for the pure Kerr case, the shadow of the pure Kerr case, because photons traveling on the direction of the black hole can approach the horizon, photons that are traveling in the direction of the frame dragging can be closer to the event horizon than photons traveling in the opposition of the frame dragging. This leads to a shadow for the black hole that are I don't know the word for that. It have a slightly flattened region, like not a perfect circumference, like this would be for the Schwarzschild case. And for the swirling case, which we will discuss the Kerr swirling, but for the Schwarzschild swirling that has been studied before, they have shown that by setting the swirling universe, the shadow becomes slightly more prolate and then twisted. And this twisting effect is stronger for an observer that are setting on the equatorial plane. So here on in this example, the observer is also on the equatorial plane, but it doesn't need to be. Whenever you put it in within the celestial sphere, you will have a field of view. This is important. So for our case, by increasing A and J, the shadow also become more strong, more prolate and twisted, and this is mostly dominated by the presence of J. So the variation in A does not affect very much the qualitative features of the shadow. It's very much resembling the Schwarzschild swirling case, at least for non very rapidly rotating A. So when A is rapidly rotating black hole, the thing that becomes more more deformed. I will show the images soon. And yes, and this is also reflected from a rapidly rotating black hole. So here we have the lensed images for a Kerr black hole. So here's the Kerr case. I think everyone may have seen this before. And here, this is what I mean. I forgot the word in English, but this is what I mean. You have like a slightly flattened region here because of the rotation of the black hole. And as we increase the value of J, this shadow becomes slightly more prolate and twisted due to the presence of the swirling background. Here we have the observer set at the equatorial plane. And here we have, well, this is the largest value we have considered, and that might answer Carlos' question, because we are considerably far from the critical value. Well, we would require very or larger values of A, and A could not be reached, but we are considerably far from the critical value. Yeah. So, and we are okay. And here we have other set of images from an observer that are not on the equatorial plane. And here the equatorial plane is not shown. It should be this one on the equatorial plane. And here we have an observer that are around the axis. And then we have kind of, we don't see much of the twisting effect, to be honest. And then we move the observer far from the axis as well, but still not on the equatorial plane. Then we started to see more twisted. But our conclusion is that for an observer on the equatorial plane, this effect is well stronger than it is for an observer not on the equatorial plane. Yeah, and here just to do a qualitative feature on the shadow for changing the value of A. As I mentioned, this deformation of the shadow is mostly guided by the value of the change of the swirling parameter. So in the first images, for instance, we have like the pure Schwarzschild swirling case, and here we have medium case for the Kerr parameter, and this shadow are well qualitatively the same. Very, very similar. Not exactly the same, but very, very similar. So changing in A does not affect it much until we reach very rapid rotation. Then we have like this flattened region here, which we understood that as being like a very similar region that we have for the Kerr case, but everything is like twisted. And here we can see that there is a small asymmetry between the lower part and the below part, because they are not exactly a reflection here. So we can see that. But well, in summary, and I should have a slide here doing a summary about the shadows that I forgot to add, sorry. But well, basically the shadows for non-rapidly rotating black hole resembles the Schwarzschild swirling case. And basically we have a shadow that is slightly plurated and completely twisted by the presence of the swirling background. So a full summary of my presentation. So we have discussed the existence and locations of light rings, as well as the shadow of the Kerr swirling black hole. Due to the swirling background, the particle motions are put off the equatorial plane, as we have seen before, to other solutions. We found that up to 3 light rings can exist in this space-time for a small range of the swirling parameter that starts to appear at the critical value. Similar in the shadows, similar to the Schwarzschild swirling case, the shadows are twisted, always they are twisted. And for rapidly rotating black hole, we see that the flattened region also appearing. Well, everything is twisted within the black hole, within the swirling background, sorry. And that's all.
Thanks a lot for your talk and for your presentation. It was really nice. So we had a few questions already, but we have time for more. So I may actually start, but if anyone has other questions, feel free. So it's more of a curiosity, and it's kind of related, I guess, to my previous question, but is it possible to have these black holes immersed in the swirling universe, but that don't exactly respect the symmetries? Like I guess that here, like the rotating axis of the black hole is the same axis as the whole universe, and the equatorial plane also kind of. So also, since you mentioned that the asymptotics is not that easy, and there's still some effect of the black hole, so I don't know if it's even possible to find solutions that would be kind of displaced or shifted, or even less in a generic way. But I don't know if you have some insight on this. It's more of a curiosity.
I don't know precisely, because well, the solution is obtained through Ernest formulas generating and blah blah blah, and they are the axis of the swirling universe and the axis of the black hole are the same indeed. I'm not sure if you, well, probably it's possible. I just don't know how to do that, but it's probably possible to have these two things not in the same axis.
Okay.
I have no idea what this would generate.
Yeah, I mean, then I guess you can try to repeat everything you presented, but in these other cases, I suppose. But I understand that this is maybe a bit too much extrapolation, but that was the curiosity. Thank you.
Yeah, but I mean,
So-
straightforward, following the generating method, they are kind of aligned by itself, let's say. So I'm not completely sure how you do that to construct this new solution.
Okay.
But that's just my limitation on my knowledge on the method, to be honest.
Okay, thank you. So,
Rogério,
any other
I
question?
just want to say I have to go now. I have a different meeting now, but I just wanted to say thanks for the seminar. Okay, I have to go now. My apologies.
Thank you, Pedro. Bye-bye.
Bye.
So do we have other questions?
I can ask a question if no one else has a question. I can.
Yeah,
ask a
sure.
question.
Please go ahead.
So, Rogério, thank you very much for this talk. I think that exploring exact solutions and their properties is always very enlightening in general relativity because it's a nonlinear theory. So we learn a lot about nonlinearity of gravity from the nonlinear solution. So, of course, some of them might be more realistic, some of them might be a bit more academic. And well, clearly, the swirling universe as a whole, as a global space-time, is it seems to be academic. Nonetheless, a bit like the Melvin universe. Nonetheless, the Melvin universe has been, argued to be an approximation in some cases. Like, for instance, if you have a black hole in Melvin, then perhaps this describes the magnetic field in an astrophysical black hole, at least until the cutoff radius. So my question to you is, did you think about situations in which the swirling universe, not the whole universe, but parts of it, could be a proxy to some physical situation?
Well, yes, I have thought about that, but honestly, I don't have a perfect answer to that. To be really honest with you, because it's very strange, let's say, like fancy to sounds better, on the things that appears on the space-time and how things behave on that space-time are very unexpected, let's say. So I cannot really think in a in a physical scenario in which you say, okay, so we could use the swirling universe to some extent to be a toy model for that. Sure, it will not work properly in everywhere or blah blah blah, but for some very small variation this works fine. We don't have a particular answer to that yet. There is one, and this was basically brainstorming, so may not make sense, and I have no idea how to study that as well, to be honest with you. But there is one idea that I particularly think is interesting, which is and this has nothing much to do with what I have presented today, like light rings, like planar orbits, and so on. But when we look to particle motion in this space-time, and you probably have seen that, the particles on the swirling universe, they always swirl around. That's where the name is coming from, I guess. Because when you test even the swirling universe, you don't need to put black holes. Black holes make things more interesting. But if in the swirling background, the particles are always swirling around the axis, this is what happens. And this is like the natural thing that happens. If you want to have a planar orbit in the swirling universe, it's basically impossible to find physical relations for planar orbits. You would need to have no angular momentum particle, which is not very interesting. So particles will necessarily not move in a planar motion in the swirling universe. This and also you put the black hole, well, you need to find relations to have closer jobs, possible to, but also the particle swirling. That swirling behavior kind of makes me think at some stage that we, what's the English word for that? When you have, I forgot the word for that. When you have like a matter being accreted in this big structure, big jets, yes, make me kind of thinking in these AGN models, you have the matter being ejected far away. You see that scenario? Probably me missing the English words here, sorry. but the fact that you have this particle swirling in a very bounded area around the axis kind of make me think in that scenario. But honestly, not realistic at all.
Right, right. I see what you're saying. I mean, it would be a gravitational version of what people think happens in an electromagnetic interaction in these jets. There's magnetic fields as well, and I guess that that's what you are trying to tell us. Yeah,
yes, that's what I try. But it's very science fiction, to be honest.
Yeah. Anyway, yeah, I was thinking that there could be some scenarios. I was thinking more about the scenario of two oppositely rotating black holes, because there's distortion, right? So, but of course, this is also an academic scenario, but there are solutions, in fact, where you have two spinning black holes which are counter-rotating. There are exact solutions. You can actually get rid of the conical singularity between them. And I was wondering to what extent, say, the swirling universe with its natural twist, which is, of course, sourced from faraway sources, not from localized sources like the black holes, could be a proxy to that, because it's a much simpler metric. But the scenario itself I'm thinking of is already quite academic, because to black holes that are counter-rotating but along the same axis is not an astrophysical scenario. Anyway, so yeah, I think it's good to try to at least think about possibilities, and maybe there's an idea that could come and arise and make these more interesting. Anyway, so thank you very much for your thoughts.
Yeah, well, thank you.
Thanks. So do we have more questions?
I think, sorry.
Yeah, please.
No, because I never really thought about these two rotating, infinitely far away black holes and so on. But I think you have something like that for the Melvin as well, right, Carlos? Like you can show that for you kind of have a limit for two far away, I think, Heinz-Nordstrom black holes, infinitely large, infinitely far away. You have a limit in which you have the Melvin magnetic universe, right? Something like that.
Yes,
Sorry.
exactly. That's sort of the inspiration. Yes, at least close to the axis, not far away. Because the strange thing about both the swirling and the Melvin is the asymptotics, and that's where clearly it becomes unphysical for the universe where we live in. But in a kind of confined region, say around the axis, perhaps it could be a proxy to some other systems. And I think that this is precisely what happens for the Melvin, and could happen also for the swirling universe. Maybe this may be a bit more complicated because we're talking about spinning black holes, but still, could be something to try to deepen a little bit. Yeah, it's not something completely, far-fetched. Two spinning black holes, equal mass but opposite spins, they would lead to some region in between them which would twist the space-time in the same way that this seems to be doing, and this should be valid close to the axis. So perhaps there is a kind of a use of this space-time as a proxy to that system. But as I've said, unfortunately, the system is itself quite academic, because it would mean two black holes that are coaxial, and this doesn't seem to be a very astrophysical scenario. Nonetheless, it is interesting for various reasons, in particular to assess spin-spin interactions between black holes in general relativity in fully nonlinear theory. So, I mean, there are some uses, perhaps. And I was just kind of brainstorming a little bit about that, but without having thought too much about it, too.
Yes, thank you.
Thank you.
Thank you. So, any other questions? So maybe I will ask a final one, since this talk seems to be approved by your cat. What's the name of the cat?
So this is Irving saying, "Oh, why do I take this blur off?" Well, just come to the camera.
But we can see it. Very cute. So I think, and this will boost our views on YouTube. So I think we will stop it here. I will stop the recording first. But yeah, once again, thanks a lot for your talk and for being with us.
Thank you.
Yeah, thank you.